projects. In this video, we are going to explain about the project titled YARS IDS, a novel IDS for multi-class classification. Introduction. The project emphasizes IDS intrusion detection system has crucial components in ensuring safety and security within the internet landscape. As internet usage continues to grow, IDS play a pivotal role in identifying and mitigating various threats and attacks. They function as vigilant gatekeepers, monitoring network traffic and detecting suspicious or malicious activities. Within the project's context, the emphasis is on the need for IDS to not only detect potential threats but also to swiftly alert administrators or relevant stakeholders. This emphasis on efficiency ensures that threats are identified promptly, enabling quick responses to prevent or mitigate potential damages caused by cyber attacks. Traditional machine learning based IDS approaches have limitations when dealing with the complexity and sophistication of modern cyber threats. The project introduces two deep learning based IDS models, YARS IDS and YARS IDS 2, aiming to overcome these limitations. Deep learning techniques offer more advanced and adaptive capabilities in identifying patterns and anomalies within network data, enhancing the overall effectiveness of IDS. YARS IDS and YARS IDS 2 have undergone rigorous training and testing using established benchmark datasets like NSL KDD and UNSW NB15. Through this evaluation process, the project demonstrates that these DL-based models outperform traditional ML-based IDS system in terms of classification accuracy and detection rate. This validation solidifies the potential for practical application in real-world scenarios. YARS IDS 2, an advancement over YARS IDS, incorporates a temporal convolutional network (TCN) into its architecture. This addition enables the model to capture and analyze temporal characteristics within network data. By considering the temporal aspect of data, YARS IDS 2 enhances its ability to understand and respond to evolving threats that may change over time, providing a more comprehensive and adaptable defense mechanism. Objective. The primary aim of the project is to introduce innovative intrusion detection system models that utilize deep learning techniques. Specifically, these models are designed for multi-class classification of attacks. By leveraging deep learning, the project seeks to develop more sophisticated and adaptive systems for identifying and categorizing various types of intrusions in network data. The project addresses the shortcomings of conventional machine learning based approaches in IDS. By employing deep learning techniques, it aims to surpass these limitations, particularly in terms of accuracy and detection rates. Deep learning's ability to handle complex data patterns and nuances is expected to enhance the performance of IDS significantly. The project concentrates on two specific deep learning based IDS models, YARS IDS and YARS IDS 2. These models stand out due to their utilization of various deep learning architectures, including one-dimensional convolutional neural network (1D-CNN), bidirectional long short-term memory (BILSTM), and temporal convolution network (TCN). This amalgamation of architectures suggests a comprehensive approach to capturing diverse features within network data for improved intrusion detection. YARS IDS and YARS IDS 2 undergo rigorous training and evaluation processes using benchmark dataset like NSL KDD and UNSW NB15. This step is crucial in assessing the performance metrics, including accuracy and detection rates, and comparing them against traditional ML-based IDS approaches. It allows for a quantitative analysis of the effectiveness of the DL-based models. The ultimate goal of the project is to provide more accurate and efficient IDS models. These models are intended to effectively detect and classify different types of attacks in real-world scenarios. By improving accuracy and efficiency, the project aims to contribute to better cybersecurity measures, enabling timely and precise responses to diverse cyber threats. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are: application is Anaconda, primary language is Python, front-end framework is Flask, backend framework is Jupyter Notebook, database is SQLite 3. Front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules of flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This initial step involves importing necessary Python libraries or packages required for data handling, processing, visualization, machine learning, and deep learning tasks. Commonly used libraries like Pandas, NumPy, Matplotlib, Seaborn, Scikit-learn are imported at this stage. Exploring the dataset. KDD Cup 99, NSL KDD, and UNSW NB15. These are well-known benchmark datasets extensively used in the field of intrusion detection research. KDD Cup 99, NSL KDD, and UNSW NB15 contain network traffic data with labeled instances of normal and various attack types, aiding in the development and evaluation of intrusion detection systems. Data processing. Pandas data frame. Pandas data frames are utilized for efficient data manipulation and analysis. These data structures allow for easy handling of tabular data, which is vital in pre-processing and feature engineering. Keras data frame. Keras is a high-level deep learning library that can work seamlessly with Pandas data frames, facilitating the integration of data preparation steps with deep learning models. Dropping unwanted column. This step involves removing irrelevant or redundant columns of features from the dataset. Unnecessary columns can hinder model performance or introduce noise, so dropping them streamlines the data for better analysis and model training. Visualization using Seaborn and Matplotlib. These are Python libraries used for data visualization. Seaborn offers a high-level interface for creating attractive statistical graphs, while Matplotlib provides a wide range of plotting functions for detailed customization of visualizations. Visualization aids in understanding data distributions, relationships between variables, and potential patterns. Label encoding using label encoder. Label encoding is a pre-processing step used to convert categorical labels, textual data, into numerical format, which is often required for machine learning algorithms. The label encoder from Scikit-learn library will be used here to transform categorical data into numerical representations. Feature selection using select percentile using mutual info classify. Select percentile, it's a method from Scikit-learn used for feature selection. This method selects the top percentile of features based on a specified scoring function. Mutual information is a measure used to determine the mutual dependence between two variables. In this context, it's employed as a scoring function with select percentile to select the most informative features for model training. This step helps in choosing the most relevant features that contribute significantly to the model's predictive power. Splitting the data to train and test for deep learning and taking X and Y for machine learning. This step involves dividing the data set into separate subsets for training and testing purposes. For deep learning models, the data is typically split into training and testing sets to assess model performance. For machine learning, X features and Y labels are typically separated, preparing the data for supervised learning. Sampling the data using condensed nearest neighbor. CNN, condensed nearest neighbor, is an undersampling technique used to reduce the majority class instances while preserving the minority class instances. It aims to create a more balanced data set by selecting a subset of data points that adequately represent the dataset's classes. Building the model. The project constructs a versatile architecture incorporating temporal convolution networks (TCN) for temporal pattern recognition, LUNet plus BiLSTM for spatial and sequential analysis, multi-layer perceptron (MLP) for intricate feature learning, support vector machine SVM for efficient classification, and ADA boost for ensemble-based refinement, creating a comprehensive intrusion detection system capable of identifying and classifying diverse network intrusions. Training the model. In this phase, the model is fed with the training data to learn patterns and relationships between features and labels. The model iteratively adjusts its parameter to minimize the difference between predicted and actual outcomes. This step is essential for the model to learn from the provided data. Flask framework with SQLite for sign-up and sign-in. Flask is a Python-based web framework used for developing web applications. It likely handles the backend of the application, including URL routing, request handling, and responses. SQLite is a lightweight database used in applications. In this case, it manages user authentication, sign-up and sign-in with the Flask web application, storing user credentials securely. User gives input, has feature values. This step involves users providing input values representing features required for intrusion detection. These input values correspond to network data attributes that the model requires to make predictions. The given input is pre-processed for prediction. The user-provided input data is pre-processed to align with the format required by the training model. This step ensures that the input data is in the same format and structure as the training data used by the model. Trained model is used for prediction. The pre-processed input data is fed into the trained model to make predictions or classifications. The model utilizes its learned parameters and patterns to predict the outcome based on the provided input. Final outcome is displayed through front end. The predicted outcome or classification is then displayed to the user through the front end of the application. This involves showing the detected intrusion type or a security-related decision based on the model's prediction. Algorithms used to implement this project, we have utilized the following algorithms. The first algorithm is TCN, Temporal Convolutional Network. TCN is a deep learning architecture specifically designed for sequential data processing, known for its effectiveness in capturing temporal dependencies within sequential data. It utilizes a series of convolutional layers with dilated convolutions, enabling the network to capture long-range dependencies efficiently. TCN is utilized within the YARS IDS architecture to enhance the model's ability to understand and analyze temporal patterns within network data, making it effective for intrusion detection tasks involving time series data. LUNET plus BiLSTM. LUNET, an architecture combining CNN and BiLSTM, convolutional neural network, and bidirectional long short-term memory, leverages both CNN's feature extraction capabilities and BiLSTM's ability to capture sequential information bidirectionally. This hybrid architecture combines CNN's ability to extract spatial features from network data with BiLSTM's capability to capture temporal dependencies. It aims to improve the model's understanding of both spatial and sequential patterns in intrusion detection tasks. MLP, multi-layer perceptron. MLP is a classic feed-forward neural network consisting of multiple layers of nodes or neurons. Each neuron in one layer connects to every neuron in the subsequent layer, allowing it to learn complex patterns and relationships in the data. MLP is used as a standalone architecture or as a part of the ensemble for intrusion detection. It's effective in learning complex relationships between features in the dataset, contributing to the model's ability to classify different attack types. SVM, Support Vector Machine. SVM is a popular supervised learning algorithm used for both classification and regression tasks. It works by finding the optimal hyperplane that separates different classes in the feature space with the maximal margin. SVM is a powerful algorithm for intrusion detection due to its ability to handle high dimensional data effectively. It is used as a classifier within the system, particularly for binary or multi-class classification of network attacks. ADA boost, adaptive boosting. AdaBoost is an ensemble learning technique that combines multiple weak learners to create a strong classifier. It iteratively adjusts the weights of misclassified instances to focus on difficult to classify data points. AdaBoost is employed as an ensemble method to combine several weak classifiers, improving overall model performance in identifying various intrusion types by emphasizing harder to classify instances. As an extension, we applied an ensemble method combining the predictions of multiple individual models to produce a more robust and accurate final prediction. Comparison graphs. Comparison graphs offer a visual breakdown of how a model performs across essential evaluation metrics. In this project, we have utilized KDD Cup 99 dataset. This dataset was one of the early benchmark widely used in the field of intrusion detection. It was created based on the data collected during the 1999 DAPA Intrusion Detection Evaluation Program. The dataset contains various types of network traffic, both normal and attack instances recorded in a controlled environment. It encompasses multiple attack types, including DOS, probe, R2L, and U2R, making it suitable for evaluating intrusion detection systems' performance. These are the comparison graphs of KDD Cup 99 dataset. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. On the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions. True positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Comparison graphs of NSL KDD dataset. In this project, we have also utilized NSL KDD dataset. NSL KDD is a refined version of the KDD Cup 99 dataset. It addresses some limitations of the original dataset, such as redundancy and irrelevant records. NSL KDD offers a more balanced distribution between normal and attack instances, ensuring a more realistic representation of real-world network traffic. It's commonly used for developing and benchmarking intrusion detection systems due to its enhanced quality and reduced redundancy. Models are compared with the parameters accuracy, precision, recall, and FN score. In this project, we have also utilized U1SW NB15 dataset. These are the comparison graphs of U1SW NB15 dataset. The UNSW NB15 dataset is a contemporary dataset curated for network intrusion detection research. It was created based on real-world traffic captured from a representative network environment. This dataset contains a diverse set of attacks, including DOS and shellcode, among others. UNSW NB15 is notable for its diversity, reflecting modern network behaviors and challenges, making it suitable for training and evaluating intrusion detection models in current network environments. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are model files which contain algorithm information which will be loaded into the project code during runtime. These are notebook.ipynb files. These are Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So here I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, this localhost, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered myself. So click on sign in. So here we need to enter the username and the password which we have created and then click on login. We have logged in successfully. So we can execute the project using 3 different data sets. Now click on prediction link. Here we can see all 3 data sets, KDD Cup, NSL KDD, and UNSW NB15. First, we will execute the project with KDD Cup. So click on it. So here we need to enter all these parameters to predict whether attack is detected or not. Before entering the parameters, let us understand the parameters. So here the first one is protocol type. It specifies the network protocol used in communication. Service indicates the type of service requested or utilized. SRC bytes, that is source bytes, represents the number of bytes transmitted from the source. DST bytes, that is destination bytes, represents the number of bytes transmitted to the destination. Logged in indicates whether the user is logged into the system. Count represents the number of connections or instances observed. SRV count, that is service count, represents the number of services used within connections. SRV different host rate represents the rate of connections to different hosts for a specific service. Different host count represents the count of different hosts contacted. Different host SRV count represents the count of services for a destination host. DST host same SRV rate represents the rate of connections with the same service to a destination host. DST host same SRV rate. represents the rate of connections with the same service to a destination host. DST host different SRV rate represents the rate of connections with different services to a destination host. DST host same SRC port rate represents the rate of connections to the same destination from a source port. DST host SRV different host rate represents the rate of different hosts for a service on a destination host. So here we will enter all these parameters now. So I'm entering the parameters. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is DDoS, distributed denial of service. Now we will enter another set of parameters and check whether attack is detected or not. So here I'm entering the parameters. So here I have entered another set of parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is probe. Now we will enter another set of parameters. So click on prediction and click on KDD cup. So here I'm entering another set of parameters. So here I have entered another set of parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is R2L. Now we will enter another set of parameters. So I'm entering the parameters. So here I have entered another set of parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is U2R. We will enter another set of parameters and check whether attack is detected or not. So I'm entering the parameters. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is no attack detected and it is normal. In this way, by entering the parameters, we can predict whether attack is detected or not. And if attack is detected, what kind of attack is detected? DDoS, R2L, U2R, etc. Now we will do the prediction with another data set. So click on NSL KDD. So here we need to enter all these parameters to predict whether attack is detected or not. Before entering the parameters, we will understand the parameters. The first parameter is service, indicates the type of service requested or utilized. Flag represents the status of connection. SRC bytes, that is source bytes, number of bytes transmitted from the source. DST bytes, destination bytes, number of bytes transmitted to the destination. Count, number of connections or instances observed. Server rate, rate of connections with SYN errors. Same SRV rate, rate of connections to the same service. Different SRV rate, rate of connections to different services. DST host SRV count, count of services for a destination host. DST host same SRV rate, rate of connections with the same service to a destination host. DST host different SRV rate, rate of connections with different services to a destination host. DST host server rate, rate of connections with SYN errors to a destination host. So here we need to enter all these parameters. So I'm entering the parameters now. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is no attack detected and it is normal. We will enter another set of parameters and check whether attack is detected or not. So I'm entering the parameters now. So here I have entered another set of parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is U2R. Now we will enter another set of parameters and check whether attack is detected or not. So I'm entering the parameters. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is R2L. In this way, by entering the parameters, we can predict whether attack is detected or not. And if attack is detected, what kind of attack is detected? Whether it is R2L, U2R, DDoS, or normal. Now we will do the prediction with another data set. So click on prediction link here. So now we will do the prediction using UNSW NB15 data set. So here, before entering the parameters, let us understand the parameters. So the first parameter is duration, time duration of connection. SB bytes, that is source bytes, number of bytes transmitted from the source. D bytes, that is destination bytes, number of bytes transmitted to the destination. Rate, transfer rate of connection. STTL, that is source time to live value set by the source. DTTL, destination time to live value set by destination. S load, source load, traffic load sent from source. D load, that is destination load, traffic load received at destination. D inc PKT, that is destination IP packets, number of packets received at destination. S mean, source mean, average value of the data sent from the source. D mean, that is destination mean, average value of the data received at the destination. CT state TTL, connection state time to live, state of the connections and its time to live value. So now we will enter all these parameters. So I'm entering the parameters now. So here I have entered all these parameters. Now click on predict button. So here we can see we got the result. There is an attack, no attack detected, and it is normal. Now we will enter another set of parameters and check whether attack is detected or not. So click on prediction link and go to UNSW NB15. So here I'm entering another set of parameters. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. In this way, by entering the parameters, we can predict whether attack is detected or not. Now click on sign out button. Conclusion of the project. YARS IDS and YARS IDS 2 models outperform traditional machine learning based approaches and even other deep learning models in effectively classifying multiple types of attacks simultaneously. This improvement signifies their superior ability to distinguish and categorize various intrusion types accurately. Both YAS IDS models have undergone training and testing on recognized benchmark datasets like NSL-KDD and UNSW NB15. Their high classification accuracy and detection rates on these datasets indicate their robustness and effectiveness in handling diverse and complex real-world network traffic. The incorporation of multiple DL architectures such as 1D CNN, convolutional neural network, BiLSTM, bidirectional long short-term memory, and TCN, temporal convolutional network, in the proposed models allows them to capture both spatial and temporal information effectively. This combined approach enhances the model's capability to comprehend complex patterns and relationships within the network data. The project underscores the potential of DL-based intrusion detection system IDS model in addressing the challenges of real-world intrusion detection scenarios. By showcasing superior accuracy and detection capabilities, these models demonstrate promise in enhancing security measures in practical network environments where timely and accurate threat detection is crucial.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.